Hello guys, today I wanted to make a video about GANs. And you might have heard this word before, and I'm just going to write it down on the screen.
Okay, I'll show you a few really nice examples of what GANs do. So there's a site called thispersondoesnot.com. So this site, it will generate, so you can see this looks incredibly lifelike, except it's not really a person. And then if you look closely in this description, it says, imagined by a GAN. So they used GANs, they used artificial intelligence to make these faces. It's seriously amazing, and you can save these images and use them. But that's not the point. The point is that GANs are these really versatile tools which can be used to generate these really amazing images.
Okay, anyways, what is a GAN? Well, a GAN stands for Generative Adversarial Network. Not network, wait, network. Okay. So let's talk about what each of these parts mean. So let's talk about what generative means. So generative means that GANs generate content, like images. I'm just going to draw a nice little swirly design. And that's what GANs are primarily designed to do. Now let's talk about the second part, which is adversarial. So this part might be a little bit confusing, but what an adversarial network is, we could use the word adversary. And an adversary is usually like an enemy or someone you compete with. And so that basically means that GANs are these networks which compete with each other in some way. And the network part, I think that's pretty obvious. GANs rely on neural networks. And I'm just going to draw a nice little depiction of what a neural network would look like. And so let's talk about how GANs look. And I'm just going to shrink this down a little bit. Okay. So let's talk about the parts of a GAN. A GAN has two parts, a generator and a discriminator. A generator, what it does is it generates new images. And what you give the generator, because it's a network, you usually give something to it. It doesn't really make sense to give something to something that makes, but in this case, we actually give these latent factors, which is basically just a list with a couple of numbers in it. We don't really know what these numbers do, hence we set them to random values. But this generator will somehow use these numbers to generate images. And so right now you might be asking, well, how does the generator generate these images? How does it create these really good, realistic images? And so that's where the discriminator comes into play. The discriminator categorizes the images as true, as real, or fake. Real meaning it's an actual image that's part of the dataset, or represents the dataset, and fake means it's been made by the generator. And so the discriminator's job is to kind of detect that. And so what happens with a GAN, and this is where the adversarial part comes into play, is that the generator tries to make images which fool the discriminator, and then the discriminator tries to recognize the generator's images. And so what happens is we pit these two different models together, and in the end we get a generator which is really good at generating images, and we get a discriminator which is pretty good at classifying them. And so what we usually do afterwards is we discard this discriminator and we just ship the generator out. And so we would just give this part out. And so the GAN is kind of like the system of how it trains, I guess. And so let's go into this, let's go into it a little bit more detail. Let's talk about how the training would happen, I guess. So what happens is the generator, it's the model, right? We give some random noise to it, which are these latent factors, these little variables, little lists of numbers. which influence what the generator makes. And again, as I've stated before, we don't really know what each of these parts of this list, of this vector, I guess, influence the generator, but all we know is that it does, and we don't really need to care about that. There are certain cases where you do, but in this, let's say, most basic example where you just want to generate images which represent the dataset as a whole, these latent factors don't really matter as much. So what we do is we pass these to the generator. I'm just going to write it as gen and put a little box to let you know it's a neural network. And then this generator will create an image. And this image is not so good. It's just probably random noise at the moment. And so you might be wondering, hey, wait, what happens next, I guess? Well, that's where the discriminator comes into play. So now that we've gotten this random image from the generator, we can kind of mark it. We can say 0, that it's fake. We can put a label 0 for fake, 1 for real. And we set this image to 0, which means fake. Okay, now what? Now we get an image from our data set. Just gonna put a nice little mountain here. And we can put the label 1, which means real, I guess. And now, what happens is you actually make the generator get a lot more images. You have to make the amount of images that are in the batch. So let's say you had 3 real images in the batch that you're giving to the model. Then you'd have to make 3 fake images, I guess. 3 fake. Now, what you do is you take these images, of these real images, just put 1s, and these fake images, just mark them as 0s, and you feed this to the discriminator. And the discriminator, it'll just train for a small amount of time. It just trains for 1 epoch, actually, for now. I'm just going to put a little gear to say it's training. Okay, so now the generator, it's slightly better. It's slightly better at recognizing that this image is fake and this one is real. But it's only slightly, and that's okay. It's only been trained for 1 epoch. It'll get better the more we train it. Okay, so now what? We got the discriminator. We got the discriminator trained. Now, how do we train the generator, right? Well, the way I'd like to put it is we kind of use the discriminator as a loss function to rate how real or fake the generator's images are. And so the way we would do this is, I'll just illustrate an example. We give the discriminator these images, we give the discriminator these generated images. Okay, I'll just put 3 here. But then in this case, we make the label 1 for real instead of 0 for fake. And so in a sense, we kind of trick the discriminator. But we are not training it. If we were to train the discriminator, it would be a little confused. But no, we want to get the discriminator's predicted rating. So let's say this discriminator is really good at classifying these 2 images. So here the expected label was a 1. And then the discriminator probably gives a really low value, like 0.05, here 0.1, or 0.07. These are very low values. And remember, 0 indicates fake, and 1 indicates real. And these are much closer to being classified as fake than real. And so, what do we gain from this? Well, we gain that this generator is not so good at making real images, right? Because clearly, this image and this label, this image doesn't deserve to have this label, in fact. It kind of deserves to have the 0 label because the discriminator is predicting it as such. And so what we want to do is we want to fool the discriminator. We want to make an image that is so real that a discriminator would give it a high rating, right? And we kind of use the discriminator's ratings to kind of check that, right? So we can see there's a pretty big difference, okay? And we'd use some kind of loss function like binary cross entropy, which is a loss function, which I believe it's minus log of your prediction. And we would use this loss, and we would train the generator's weights. So we would feed this value to the generator. Just realize in this stage we're not touching the discriminator's weights. We're only training the generator. And so we repeat this process over and over and over again. Just again and again and again. And then in an ideal situation, you'd have this discriminator, and then we'd have these images which are really good. They're so good at pretending to be real that when we give this fake label as 1, indicating that it's real, even though it's not, we successfully fool the discriminator because it looks close enough to a real image that the discriminator cannot really tell the difference. And so that's essentially how a GAN works. And so that's really the process of how it works. And so right now, I'll be going over a little coding demonstration, practically in code, and I'll show you how to generate images using the MNIST dataset. So in the beginning, we'll have the generator make these really bad images, and then in the end, you will ideally get something that resembles a number. And so that's what we're going to work on right now. And I'll go over a really detailed and comprehensive process of how this works.
Hello guys, I'm in Google Colab and I'm going to show you a little coding example to demonstrate how the GANs work in action. And I'll show you how to make your own GANs. And let me just first put a name to this project. I'll just call it GAN example.ipython notebook, and I'll just connect to a runtime. And I'll make sure that I have a GPU runtime for the sake of speed. I really don't want to wait that much for my code to run. Let me manage my sessions and terminate this one. I'm just going to close this and reconnect. So now I can connect to a GPU runtime. Right. So I am going to be coding this GAN in Tensorflow. So I need to import it. Tensorflow as TF. Now if you're doing this on a local environment and not in Google Colab, you might have to pip install Tensorflow. Now I'm going to also import NumPy, because it makes my life easier in some cases when I want to do some manipulations of matrices and vectors and stuff. And lastly, I'm going to import Matplotlib. I'm going to make sure to put the magic function Matplotlib inline, and I think this helps with how it is presented on the screen. I'm not sure how much it helps in Google Colab, but I do know that it can help when you're using a Jupyter notebook in general. So let me just run this code right now perfectly. Now I'm going to load the data set that I'm going to use for my GAN, and in this case I'll be using MNIST. And so I'm pretty lucky to have it because Keras already has utilities for loading it into your system. And so I'm going to get my variables, and this is how the data is structured. You have an X train, a Y train, which are your labels. We don't really need to use these though. In fact, yeah. And we need to use X test and Y test. Now, in this case, I don't think I'm going to use this, I think I'm going to use the Y train, X test, and Y test. Though, in an ideal situation, I would combine the X train and X test datasets so you have the most amount of images to your GAN. Now, we got to load the data. So I'm going to do tf.keras.datasets.mnist. That's how you get the MNIST dataset. .load data. And so in this case, I'll be generating numbers because it's like the most recognizable thing you could do. But if you wanted to generate fashion apparel, you could easily switch this to fashion MNIST. Right? So we got that covered. And I'm going to convert this because by default, this is in a float 64 format. And so I gotta convert this X train into float 32. So I'm gonna convert this as type. This is how we convert these.
and we're going to reshape it because actually in this case, I want my images to be in the format 28 by 28 by 1. 28 and 28, they're the width and heights respectively, and 1 is the number of channels. This MNIST is grayscale. In an RGB image, like in a dataset like CFAR10, you would have 3 channels, but in this case I only have 1. And so the reason why I'm actually including this 1, even though it seems a little redundant, is for debugging purposes. I want to be able to just easily switch from MNIST to CFAR and vice versa, without changing much of my actual code. So the way I'm going to do this is I'm going to reshape this dataset. Reshape, not respape. Reshape. And I'm going to set this first part to -1 because I don't care how many images there are in the dataset. And I want the width and height to be 28, but then I'm just going to add this 1 as the number of channels. It just encloses every single element in the dataset with a list. So each element is kind of like a list of 1 element. And now I'm also going to downscale the image. This image is from 0 to 255, but I'm going to normalize it and I'm going to make it from 0 to 1. And I'm going to make sure that to make this a decimal 0.0, so that it keeps the result as a float, 32, and not as an integer. Right, so now I'm going to define hyperparameter batch size, because I want my data set to be in batches, right? And so I'm going to set my batch size to 128. This is kind of an arbitrary value. If you wanted, you could set this to be higher, though I don't know if you should set it to a lower value. The models will perform better, ideally, if the batch size is higher, and I think that's the case in deep learning in general. So let's move on. Now, we have to create our data set. And you might be asking, hey, we have a data set here. And so yeah, this is a data set, but it's in a NumPy list. And in this case, just to make my life easier, I'm personally going to make this into a tf.data.dataset, because it's really easy to do some operations like batching, and I want to batch my data set into a batch size of 128. So I'm just going to do that. And I'm going to make a data set from this list. We say from tensor slices for my X-train. Now I'm going to batch it with my batch size. And I don't want to have any images sticking out, because those images will kind of disrupt the shape of disrupt how the model is trained, because in this case, for simplistic reasons, I'm going to pass this batch size into my model. And so if the list of images given in the batch is not equal to this, we'll have a problem. So in this case, I'm going to drop the remainder. Okay. And I'm also going to prefetch the images, and this will just make it a little bit faster to train. And the way it prefetches, I'll set it to auto-tune. And in general, I think that's a good little tip, unless you really know what you're doing. So I'm going to create this data set. Let's see if things work well. It's loading from MNIST. And it looks like everything executed, and pretty quickly. Okay. So now I'm going to create my generator and discriminator models. And I'm actually, for organizational purposes, I will keep them enclosed in a class. So I'll just call this class GAN architecture. And all these you totally don't have to add these parentheses here. Just adding them because I like the green color of the highlighting. I wish without those parentheses I could still have that color. So now, just give me a sec. This code creates and manages architectures for the generator and discriminator. So that's nice. I'm going to create the generator, and I'm just going to actually first create a constructor, and I'm going to pass my input shape and the number of latent factors. And I don't think you remember, I hope you remember, the latent factors is like a vector with a bunch of numbers, which somehow influence the generator, and it makes it generate these new images.
And so I'm not exactly sure, and I don't think anyone is really sure for certain what these latent factors do, what each of the items in this latent factors do, and it's actually not something we have to worry about unless we want to kind of give the GAN some kind of command, like we want the GAN to generate 1s or 7s or something. Then we have to encode that in our latent factors. But here we just want to make images which represent this MNIST dataset, so all kinds of numbers. As I was saying, we want to have a number of factors in our constructor. So I'll just make some instance variables. Then, so that's great. Now we got this. Now I'm just going to create a little function for creating my generator. So in this case, this is a very simple GAN. And so I'll be relying on multi-layer perceptrons. I'm just going to use dense layers. Ideally, though, the best kinds of GANs, we call them, they are really good at generating images. I think we call them DC GANs, which means that they only use convolutional neural networks. But for the sake of simplicity, I'll just be showing you how to do them with dense layers for now. So I'll create a little model instance. And I'm just going to use the basic sequential architecture. Now here, we're going to first start with a dense layer. Just give me a sec. You can charge my iPad. I'm just going to create a list of layers. I'm going to first start with a dense layer. And this will have, I'm going to make it accept the number of factors using the input dim argument. So this is, it takes the number of factors, in our latent factor space as the input dimensions. It takes, for example, if we were to pass 10 factors, this model will accept 10. So sorry if I was being redundant, but just wanted to explain that. Okay, and so we have these number of factors, and so from these I'm going to make 100 layers as my output shape, and then I'm going to put an activation function, and in this case I'll use a leaky ReLU. I found that in my experience that leaky ReLU works a little bit better than the regular one, and I'm sure there might be some research about that as well. But in this case I'll just use a leaky ReLU. Then case, I'll create another dense layer. And in this case, I want to generate an image with 28 times 28 pixels, right? 784 pixels, right? But I don't want to hard code 784 because let's just say I change the number of pixels, the width and height of my image. This value of the dense will be different. So in this case, what I'm going to do is I'm going to take the product of the input shape, because input shape is the width by height by number of channels, which is 1. And so in this case, it's just width times height, which is basically the number of pixels. So the way I do that is I'll use this numpy.prod, which is the product. I'm going to take the input shape. So now, in this case, I'm going to make the activation of this dense function a sigmoid, because, as you remember from this step, my images are from a scale of 0 to 1. And that's what a sigmoid does. It makes things in the form of 0 to 1. So that's what I'll do right now. And now, I'm going to reshape these pixels, because now this is flattened, right? Let me just correct my typo here. I'm going to reshape it to my input shape, right? Because in this case, 784, I'm going to reshape it into a 28 by 28. We still have the same amount of pixels in both, so it works out. So I'm going to create a little generator instance in this GAN. I'm going to assign this model to a generator.
Right, and I'm going to do the same thing for my discriminator. So in our case, the discriminator, it's supposed to take in an image and return 0 if it's real or 1 if it's not. And then because models are never static like that. We don't want them to be because the gradients will be weird. So in this case, we'll give like a probability. 0 means 0% probability, 1 means 100%. And so that sounds like a very standard classification model. So we'll just do what we do in a standard classification model. In a second. Okay, now, like a regular classification model where we try to classify MNIST using a multi-layer perceptron, just a bunch of dense layers, we first want to flatten our input. And our discriminator, it will take in the image as the input. Sorry. Keras.layers.flatten. We use this flatten layer to flatten our input. And our original input shape will be the shape of the image. Right? Okay, that's nice. We're going to pass it to a dense layer. 100 units. Then we're going to create a little leaky ReLU. And as I mentioned, I personally found that leaky ReLUs work really well, or GANs. And put it in the comments if you have some kind of empirical research that kind of supports this. That would be pretty interesting for me to find. If I find anything suggesting it, I'll probably put it in the description. And anyways, our last layer, we want our output to just be one number. So I'm going to create a dense layer with only one output. And because we want it to be a probability from 0 to 1, I'm going to make my activation sigmoid. Right? And then I am going to set my discriminator. I'm going to create an instance variable discriminator which has this value. Okay, that's great. But what I want to do is I'm going to set these values. I'm going to set these values in the GAN when I initialize this class. And so you can keep it in the constructor, obviously. But what I want to do right now is it's probably, if you don't know about it, you'll learn it. I'm going to create a call method. And what happens is, like the constructor, what happens is if you can treat this class like a function almost. So it kind of helps you put functional logic in your class, which kind of eliminates the need for putting all that bulky stuff in your constructor. So I'm just going to create the generator, and this is going to assign it to the instance variable. I'm going to create discriminator. In this case, after I have the call method, I want it to return this instance of a class. You could totally just put this stuff in the constructor. You could just cut and paste it here if you want. But in this case, I just feel like doing it. I just feel like making a call method. So let me just run this. Let's just verify that this class works without any weird things happening. Interesting. I forgot to put my input shape and the number of factors. So I'll just hard code it just for testing purposes. I'm just going to put 10 as my number of factors. And as you can see, this class gets created successfully. So now I am going to create a model now. I'm going to call it GAN trainer model, and this time I'm going to inherit the models class. So I'm calling this a trainer model because I'm kind of creating it to train these two models in this GAN architecture class. So I'm going to create a constructor, and I'm actually going to pass the input shape to this GAN, the input shape and num factors and batch size into this GAN trainer model, which I will then pass here because I do need these I do need the batch size and I think number of factors for my training loop. So let me just include them in this constructor to just, kill two birds with one stone. I'm going to make a call to super because I have a constructor with these new variables. Cool. And so now I'm actually going to create an instance variable for my architecture because I want to train these models, so I need this instance. GAN architecture. I'm also going to make my batch size, num factors, and input shape. Yeah. Okay, that's great. So I'm also going to create some instance variables for some of the stuff that I use a lot throughout the training session that I don't want to be created over and over again. And in this case, it'll be my labels, my list of labels, because they stay the same throughout the training session, and I don't want to declare them over and over again. I really don't think it matters that much, also for like an ease of readability, I guess. Anyways, I'm going to create my true labels, and these are the labels I would pass to the discriminator if the images are real images or if I'm fooling the discriminator. And these will just be a list of ones, and so I'm going to use the Tensorflow tf.ones utility, which just lets me create an array of ones given a shape. In this case, my shape will be the batch size over 1, and this will make it compatible with the discriminator's input. I'm also going to create the self.false labels, which is an array of zeros. Remember, 0 means false, 1 means true. Make it zeros, batch size by 1. Because it's the same shape. In this case, I'll have the same amount of true labels and false labels. Okay, cool. And in this case, I want to keep track of two losses. The discriminator loss, which I'll name it as loss tracker. And I'm gonna use this mean metric. So what it does is it doesn't make the loss. Normally, you won't see this kind of fluctuation in loss if you were using it in a custom training loop without this class. I'm going to create another loss for my generator, and you'll see why we need to keep track of these. In this case, I want to check the discriminator loss after I train the generator. Okay? And so after I train the generator, if the loss is higher, then I will know that the generator got better at fooling the discriminator and that the discriminator has a higher error after the generator got trained. Right? So now I have to, at the end of each epoch, I have to return my metrics. So I will define that function. Self.loss tracker. I want to return my loss tracker as well as my generator loss. I almost forgot that word. Okay. And also, I want to have two separate optimizers for my generator and my discriminator. I think you could have one if you want, but I think it's a better practice to have two. So I will override the compile function because by default it only asks for one. So I will ask for the discriminator optimizer, the generator optimizer, and the loss. Okay, and so because I'm overriding this function, I have to make a call super. No, not architecture, GAN trainer model, self.compile. Right. So now I'm going to make instance variables. And The D optimizer is the optimizer for the discriminator, G optimizer is for the generator. And also, if you're still watching, thank you so much. Thanks for viewing my video, and I hope you learn a lot after this tutorial once it's finished. It's kind of weird, I'm saying it in the middle of the video, but you know. And also, I am going to keep my loss as an instance variable, which in this case is binary cross entropy. Right, so that's it. And now I'm going to make my training loop. So for each train step, which is why I'm using this function, define train step, we first want to get the fake generator images, if you remember from the video. I'm just going to take my random latent factors, so what I'm doing is I'm basically making a bunch of random values, and it's basically a list. So you have the number of images in the batch, random factors, and then for each random factor you have this instance variable number of factors inside of it. So in this case you will create a list. For example, if I have 3 images in the batch and 3 factors, this would be how my latent factors would look like, except instead of ones I would have random values. And also another thing to note is that it's very important that you use tf.random.normal and not tf.random.uniform. I personally noticed that when I used this latter one, I didn't get good results than when I used this. And I think it has to do with the distribution, the random distribution, because in a normal it's in a bell curve, and there's going to be some reason it helps the model, right? So now, using these random factors, I'm going to call my generator. Let me just do that. I call this gen images equals, I'm going to call my architecture arc.generator, because remember it's an instance variable. I'm going to get my random factors here. Right, so now I have that. I have my fake images, and as you can see, I have my fake labels. Now I'm going to get the real images, okay? So I'm going to create discriminator data, make that a variable, and what I'm going to do is I'm going to concatenate these real images, these fake images, with my real images. So I'm going to do it the other way around, because why not? And so in each train step, you get one batch of data passed. So that's how you know what the real images will look like. So I'm going to also create a variable for my labels, right? Because when I'm training my discriminator, I want the 1s for my real images and 0 for my fake. I'm going to concatenate my real labels. I'm going to call it real labels or true labels. I call it true labels. I don't like that name now. It's too late. Okay. I'm going to call them true labels and false labels. And actually, I'm going to make the axis equal 0. So it actually adds these generated images to the data. Okay. And now I'm going to train my discriminator. And in this case, I will put a little comment to let us know. Right. So I'm going to use gradient tape to train my discriminator. And it might seem a little bit weird or hard at first, but I actually really like this system, and I kind of prefer it. I think it's really cool compared to PyTorch's, because it kind of lets you declare the gradients yourself. So I'm going to set this gradient tape, What it does is it monitors the values that you use in prediction, and then you pass the gradients. You don't need to worry about what that is if you don't really understand it. Don't worry. This is basically just a lower level way to train your model. So I'm going to get the predictions of the discriminator, And then I'm going to run my loss function on this. And I'm going to get my actual labels, which are these discriminator labels, and my predicted labels, which are these. So this is basically what happens in a regular neural network training session when you call it model.fit. This is usually what happens. I think I'm grossly oversimplifying it. There's probably a lot more, but this is like the gist of it. Okay, now I'm going to get the things which I need to train. So these are my weights and biases that I'm passing the gradient. Okay, and anyway, sorry. Now I'm going to make my gradients. And you really don't need to worry. You can, if you don't really understand this, you can kind of treat it like a boilerplate code. And I'm grading the gradients of the loss with respect to the variables. Or I might be switching that around. Right? And so you apply these gradients. You use the chain rule in calculus to update the weights, but you really don't need to worry about that. This is also some kind of boilerplate code. And really the parts that you really need to pay attention to are these two lines. Right? So I got this, right? So now I got to train the generator again. So what I'm going to do is I'm going to generate a fresh set of random factors. I'm going to put a little comment here. This is the generator. I'm just going to create a little fake set of another set of random factors. And in this case, I'm going to, as mentioned before, I'm going to trick the discriminator by putting real labels for my fake images. And so, as I mentioned before, the reason was the reason is we're not training the discriminator, but we're using the discriminator as a loss function to kind of rank how good the generator's images are to the discriminator. Right? And so I'm basically going to kind of repeat this step in this case. Just let me kind of copy and paste, I guess. Because really, a lot of this is boilerplate. It's gen. So instead of discriminator print, I'm going to make a gen for generator. In this case, I will make the generator predict the discriminator predict my generator's images. Right? So I am going to get my images. And in fact, I can just copy this line, in fact, but why don't I just do that for the sake of this video? Right? Now I can make the discriminator give its ratings, how well it thinks the generator is, I guess. So now we're going to use this loss. We're going to check trick labels. We're going to see what is the difference in these trick labels and what the discriminator predicted. And if this difference is high, that means the discriminator thought these images were fake. That means the discriminator was right, and the generator was not good enough at creating real images. So we really don't want that. We want the discriminator to be pretty confused about what is real and what is fake if the discriminator is really good. That means that the generator is really good. And sorry if you're getting confused by the discriminator and generator. In this generator, got trainable variables. I'm going to get the generator's gradients, and you really don't need to worry about this if you don't know what this is. And, weird. Oh, never mind. Okay. I'm just applying this. Now, what we want to do, this is also boilerplate, but we want to kind of return these lost metrics so then they can be printed out by Tensorflow. And we first need to update our loss to return, for returning it, obviously. So I'm just going to update the discriminator loss label and the generator loss label metric. And I'm going to return these values in a dictionary, because I think that's what TensorFlow wants. Oops, I accidentally ran that, and I didn't want to. Loss. I'm going to create this generator loss. If you want, you can format this dictionary. I might as well do that right now because you guys are watching the video. To be honest, if nobody was looking, I'd probably not format it. Anyways, we have finished the training loop of this GAN, so that's good. So what I'm going to do is I'm going to train my model now. So I'm just going to first initialize my trainer, this trainer model, right? So we need the input shape, the number of factors, and the batch size. So I'm going to just define them as these constants. In this case, our input shape is 28 by 28 by 1. Remember, we're using that one extra channel because we want to expand it. At any time, we can make this 3 or 4, depending on our data set. We also need our number of factors, which is 100. And we also need our batch size, which is, in this case, actually, we already defined our batch size, didn't we? Let me just check. Did we define our batch size? Yes, we did, so we don't have to redefine that again. Input shape. Let's just check. Input shape, number of factors, and our batch size. So now we're going to compile this model, which means we're going to set the loss and the optimizers. In this case, I'm going to use binary cross entropy as my loss, and my discriminator optimizer is Atom. And my generator optimizer is, well, it's also Atom, because Atom is great. The Atom optimizer, obviously. Now let's see if everything works well. Oh, I forgot to put comma here. And, interesting. Apparently, it is saying that I forgot to put 2 positional arguments. Interesting. I'm just going to check what the issue was. Oh, here I forgot to set my input shape and num factors. The GAN architecture, right? I mentioned I would pass these input shape, number of factors. Right? Is that it? Yeah. Okay, now let's see. Let's just hope that everything works. Can't set the attribute input shape. Likely because it... I'm going to... Okay, I think I figured out the issue. I think I just I blindly set this as an instance variable. I think there's some kind of overriding that occurs when I'm setting this architecture because this one also has the input shape in it. So just give me a second to... Right. Now, the model works as expected. So now, I am going to train the model. This will be the fun part. Trainer.fit, and I will use my dataset, and my epoch number will be 20. That'll give us a good result. Okay, interesting. Getting error. Now, I think I know what the issue is. I forgot to use the word self, as I think I worked with Java a lot these days. You don't have to use the word this or the word self in this case. So let's see if that's it, or if I forgot something else. Looks like everything is working fine. So now, the reason why I wanted to check this generator loss is, if this loss keeps on getting higher, which that actually happened to me once, it's because the generator just isn't learning at all. The generator isn't being trained, and that there's a problem with that passing of information from the discriminator to the generator. And so that's why I included this little variable here, this little metric, I guess. And so let's just wait for it to train for 20 epochs. Now, obviously, you'll get better results the more you train your GAN, but 20 should give us a little sufficient result to kind of see how this works. Anyway, so now first, let's try seeing if our GAN actually learned something. The results look promising. The generator loss is getting smaller, and it's actually staying the same, which is good. That means the discriminator is also learning and compensating for that. So let's confirm it for ourselves. Let us make our own little image. So in this case, I'm only going to make one image. Okay, I'm just going to create one image, and our generator has 100 factors. But in this case, I'll use this little constant. And I'm going to use this trainer's architecture to make predictions. Okay, I have this, right? And let's give a little preview. And as we can see, this is an array of images, and so predictions were able to come out pretty well. So now let's preview this. So plot.imShow, this lets us see the image. And so we're going to get the generated images. What I'm going to do is I'm going to set this property CMap. Without it, it has this really weird color coding where things which are dark are like purple and things which are light are yellow. I personally like it when it's grayscale. Let's see what happens. Okay, it didn't work because the shape is 28 by 28 by 1. This is actually expected. I was expecting this to happen, so I could teach you. Matplotlib would like it if the images are in 28 by 28, or if it's grayscale, or 28 by 28 by 3. It doesn't like this kind of middle ground between those two. So I'm going to remove this little one by, I think, reshaping it. What happens if I just do reshape? 28 by 28. Right. This is a TensorFlow tensor. I can't use NumPy, so I'm going to use tf.reshape. I'm going to reshape this to a 21 by 28, actually 28 by 28. Now let's see what happens. Okay, this doesn't look like a number, but it doesn't look like random noise. It looks like the generator learned that numbers equate to squiggles. And so that's good. We're getting somewhere. If we train for more than 20 epochs, let's say like 40 or 50, we'll probably get better results. Okay, there you go. We got something. So this looks like a 4, which is great. I'm going to try again. This looks like the generator is mixing numbers together. This simultaneously looks like a 0, an 8, and a 6 at the same time, which I think that's personally really cool. And so there you have it. We've successfully trained this GAN. And so obviously you can train it for more than 20 epochs if you want. I'm just going to run this again because I'm really interested in this. This looks like the letter A. Anyways, as I was saying, you can train this for more than 20 epochs if you want. And actually, I might go over some more optimization methods to get a better result with the GAN. I think, as I mentioned in the explanatory parts, you can use this thing called a DC GAN, which uses convolutional neural networks, and that usually gets you better results, but for MNIST, this looks sufficient. And in fact, what you can do is you can literally just drop in replacement, add the word fashion in MNIST, and you can get a GAN that generates apparel. And so I'll share this little Colab notebook with you guys, and if you want, you could change it. So I'll just include in the comments you can change to fashion MNIST. Right. So that should be it for the coding part. And so, guys, thanks for letting me show you this. And I have to edit this video, and I'll probably cut a lot of these parts at post. This is like, what, 53 minutes? This is a behemoth of a video. But anyways, thank you. And, yeah, bye.